In a circular motion, there is acceleration, yet the speed is constant. Explain. I said because of change in direction. In as much as the body is moving with a uniform speed, but the instantaneous change in direction. You see the direction is changing as that body moves. At this point, it's moving in that direction that is happening. Remember, acceleration is a vector quantity, meaning there is magnitude and direction. So the magnitude may not be changing, but because the direction is changing, therefore the body is considered to be accelerating. I talked about it at the start when we were starting this topic. Yeah. So explain how a centrifuge, so in this case, is used to separate cream from milk. So in this case, remember we talked about the centrifuge pale, and we said different particles in a given liquid that you want to separate with particles that needs to be separated. Different particles will be having different masses, and therefore they'll be experiencing different centripetal force, you see. So cream and milk will have, or definitely have, different masses, and therefore they experience different centripetal forces. There is different centripetal forces acting on cream and on milk. But before you answer this question, I just want you to go and watch a video on centrifuge. Somebody needs to mute. I'm not so sure who that is, but try mute if you're the one. Yeah, so please watch that, and then maybe later on as we, because we are going to discuss this again during our sessions next week as we revise. It will be part of our discussions. Then number 3, an astronaut in orbit around the Earth may feel weightless, even when the Earth's gravitational field still acts on him. Explain. Somebody needs to mute. There is somebody there who's supposed to mute. Okay, the one place mute. So this is the case here. This, the astronauts, they reach a point whereby centripetal force is balancing with their weight. Centripetal force is balancing with their weight. Centripetal force is acting in this direction. Yeah. So they'll not be experiencing their weight. Yeah. Remember we said at this point, there was weight acting downwards. Weight acting downwards, or what we call mg. And then there is tension acting in that direction. So if you have to look at the resultant force on that, there is centripetal force acting in that direction. Centripetal force acting in that direction. So if you look at the resultant force experienced by this object, because now the reason why I'm looking at the force experienced by the object is because this person, the examiner here is talking about the astronaut in an orbit around the Earth is feeling. So it is the weight that is experienced by the object. You see, now we're not looking at the resultant. We are looking at the weight experienced by the object. You see, it's slightly different from what you are looking up there. So in this case, it is the weight experienced by the astronaut, the object here. So this weight experienced by this person could either be dragging them in that direction or dragging them in that direction. So in this case, when you say that they are feeling weightless, it means that the resultant force acting on them is 0. That's why they're not feeling any weight. The resultant force acting on them is actually 0. So we are saying centripetal force minus the weight, that is the resultant force acting on them. Centripetal force minus the weight is equals to 0. So that case, what you can talk about is that the centripetal force, because they're moving around they're moving around the Earth, the centripetal force is balancing with their weight. So their weight is overcome by the centripetal force, or rather, the centripetal force acting on them is equals to their weight. In fact, that is another way of looking at it. Yeah. The weight of this astronaut is equivalent to the centripetal force that is acting on them. And therefore, they are not feeling any weight, or their resultant force, or the resultant force acting on them is 0. Distinguish between angular and linear velocity. We already talked about that. Angular velocity is the rate of change of angular displacement with time. Linear velocity is the rate of not linear, but the rate of change of displacement. Okay. I don't know whether I need to admit them to the other class. That's why they are talking. Yeah. Okay, fine. So, because of that bit of contradiction, you can see I'm talking about angular displacement. How will you call the other displacement? So what I would advise in that case, if you're distinguishing between, because remember when you are dealing with linear displacement, when you're dealing with linear motion in form 3 work, we talked about linear velocity. We talked about velocity as rate of change of displacement with time. But in this case, now we have two displacements. How will you differentiate between the two? That is the challenge we are now facing here. So in that case, I would advise, or I would propose, that talk about angular velocity as the rate of change of angular displacement with time. But when it comes to linear velocity, you talk about speed in a specified direction. Just that. Speed in a specified direction. So that don't talk about displacement, otherwise it will appear so contradictory. Because the angular velocity is the rate of change of angular displacement with time. But what about linear velocity? Will you say linear velocity? Will you say linear displacement? Anyway, so talk about speed in a specified direction. I think that will define, because that is still a valid definition of linear velocity, speed in a specified direction. How is centripetal force different from any other force? A centripetal force is directed towards the center of a circular path. Force is experienced by a body that is moving in a circular path, and then it is directed towards the center of that circular path. Now you can see a stone is whirled with a uniform speed in a horizontal circle having a radius that it takes the stone 10 seconds to describe an arc of length 10 centimeters. Calculate the angular velocity. So you see now, in this case, you have to find the relationship between angular velocity and linear velocity, because we are given linear velocity. When you are given these, you are told it takes 10 seconds for that stone to describe an arc length of 4. This is linear velocity V. So V is equals to S over T, or S over T. So S is the one that is given as 10. And I said you can multiply it by 10 power negative 2. And then you divide by time, which is 10. Actually, it is supposed to be 4. This one is supposed to be 4. The displacement here is supposed to be 4 centimeters. So you divide by 10. So that is 4.0 times 10 power negative 3 meters per second. That is linear velocity. So we are looking for angular velocity. If you go back to the formula chart there, we said angular velocity is given by linear velocity over the radius. So you have to check. So linear velocity is 4.0 times 10 power negative 3 divided by the radius. What is the radius of that circular path? 10. So you divide by 10 times 10 power negative 2. So that is going to be what? So that is going to be 4.0 times 10 power negative 4. The unit was rads power negative 1, radians per second. Radians per second. Yeah. So you need to practice just highlighting the formula. Linear velocity of the stone, we have done it. Angular velocity, the periodic time. Yeah. So periodic time, you can remember there is another formula we talked about. Somebody's already exiting class. I said we'll extend by just a few minutes. So angular velocity, periodic time, you can remember there's another formula we talked about. Periodic time is given by 2 pi what? 2 pi f. Yeah. 2 pi f. So it means you need to get this. There's even another formula that was talking about 2 pi over omega. So it's about identifying the right formula to be used. Once you identify the right formula, you simply substitute. It becomes very easy. So that is 2 pi divided by what we have just gotten, 4.0 times 10 power negative 4. And you'll be able to get the answers. So what I would advise here is that after this lesson, try and practice and practice and practice and practice. This topic is usually easier. The reason why it is easier compared to others is because you only need to remember the formula. As long as you can remember the formula, you're good to go. There is not so much explanations when it comes to this topic. Actually, majorly it is math. It is majorly math. So if you are very good in math, like I normally assume that those who take physics, they are equally good in mathematics, then this topic will be a topic of choice, or rather a more preferred topic for you, because it's majorly mathematics. If you look at even the questions that are tested, right from question 1 to question 12, the ones that are displayed on the screen, you can see it's 90% mathematics. Maths. And maths here, just ability to remember the formula, nothing else. The proofs will come later on, maybe when you get to colleges and universities. That's when we'll start asking you about the proofs. Prove how we are arriving at the formula 2 pi over omega. We hardly test. It's not tested that much. We hardly test. In fact, just try and go through past papers, try go through KMF. You realize that most of the concepts that are tested is just about remembering the formula and getting to know what the conventional symbols represent in the formula. And just that. So I think that is all. We can stop it at that for today. So next week, we are going to resume the whatever revision that we did last time. And this is also going to form part of it. Part of it. Just like we said, we just take you through the topics. And then as we revise the topics we have covered, like now we have covered 2 topics so far. Thin lenses and this other one. At least now you have an idea. So as we revise next week, as we go through the papers, these will also form part of that revision. Otherwise, that is all for today. Until next time, have a good day ahead. Goodbye. Okay, Maya, have assigned you your class. You can see Sasha. There is Kiswate here. Teacher.com. We used teacher.com last time, so I'll still use that. Oh, there is Hope. You've been assigned that class. Okay. Let me see. ALB Physics Book 2. Somebody here says, Hope I already assigned your class. You just need to tap and join.
Tap and join. Tap and join.
Oh, there is Lorna here. There is who else? Rosemary. Okay. Oh, there is Hope Janelle. I'm almost there. I'm trying to access book 2. Okay. Francis Ukela is saying, teacher, you need to admit me. Yeah, done. So Hela, it is done. Just tap and join. That book is taking long. Let me get it from Teacher's Arena. It's really taking long to open. Control F Physics. Physics book 2 KLB is here. It's really taking long to open from the other end. I don't know why. But let me get it from here. That's why it's always good to have an alternative. And finally, we got it. It is here. This is even faster. I think I can be using this. So you did magnetism the other week. So this week we have been doing measurement and we did vernier calipers. Oh, we did vernier calipers and micrometer screw gauge. Now I know today you know how to take the measurements, how to capture the readings. We even did the zero error. The challenge is usually Bridget is requesting to be admitted to Form 3. Oh, there is Saida. And these people, have they really joined? There is also Hassan and Patience who have not returned. Saida, okay, fine. So now, we are like almost done with that because we did vernier calipers, you know how to read it now. We did micrometer screw gauge, you know how to read it, because that is what will be tested in the exam here. So hizi zote tumefanya zote. Significant figures you have done in math. If you have not done significant figures in math, you can type somewhere, not yet. Just type in the chat. If you have not done significant figures, you have done standard form in Form 1, maths. Yeah. I'll touch a bit on prefixes, kidogo, and then I'll go to revision. Prefixes. I know there are sometimes when teachers don't teach prefixes used with SI units. Yeah, so I'll touch on that a bit. Significant figures, I know you have done in math. If you haven't, please type somewhere you don't know what a significant figure is. Like if I was saying, write your answers to 4 significant figures, 2.437. Yeah. If you don't know what that is all about, please type in the chat. I can't see anybody here who is supposed to be admitted. So you see now, that means I just want to touch on prefixes used, and then I will go into revision straight away for revision for this topic. Because like we have covered, because we covered vernier calipers, or there is something else I didn't do last time called the thickness of an oil molecule. I think that one also I need to do the first 30 minutes. You can see we have 20 minutes to do that. So let me touch on that a bit. Yeah. Oh, Zippy says they need to be admitted to the other class. Zippy is here. Or even Rufaida. Okay. Zipporah is saying, teacher, admit me to the other class. Okay, done. So, magnetism we did magnetism. So measurements. Under measurement 2, we have done vernier calipers and micrometer screw gauge. And I said vernier calipers is used for convenience. Micrometer screw gauge is used also for convenience, yes, but it's majorly used for small, very tiny measurements. And we looked at how we take the measurements using a micrometer screw gauge, how we capture the readings. We did all this, This is what we did. We did the zero error. So please take note of the zero error. Somebody will ask you to explain what zero error in a vernier calipers is. So the jaws closed, but no object in between. The zero error on the vernier scale and on the main scale should coincide. So if the instrument is considered to have a zero error if the zero mark is not coinciding, the zero mark on the main scale is not coinciding with the zero mark on the vernier scale. I already talked about that. For the micrometer screw gauge, the zero mark on the thimble scale, is not coinciding with the center line. Remember I talked about the center line last time? Yeah. I can see somebody has joined here. This is Lian. Yeah. So we already talked about that. We talked about the pitch, the zero error. Again, I used, when you are asked to state whether the zero error is negative or positive, you look at the zero mark on the main scale if it's on the right. But let me use positive. It's on the right. Zero mark on the main scale is on the right. Then that zero is the zero on the right of zero mark on the vernier scale, like in this case here. This is usually tricky for most students. That's why I'm giving you a formula of telling whether it is negative or positive. Normally, it is very hard to tell whether it is positive or negative. So this is how you tell. You just take the zero mark on the main scale. AMBA says it is on the right, and that is negative. AMBA is requesting to be admitted. Even AMBA is requesting to be admitted to the other class. I think even Mulimi Masi. Yeah, Mulimi Masi is also requesting to be admitted to the other class. I think you requested last time. So, and then that is negative. And then when you come to micrometer screw gauge, the same thing. So negative. Now here you check the center line. You check the center line. So you see the center line is here. It is above. Above the zero mark on the thimble scale. Yeah, so that is negative. Negative. So please take note. Take note. Yeah, so that is what we discussed majorly. I think that is what we finished with last time. And significant figures, I said you've done it. So I will not do it. We will maybe capture it during our revisions. If you've not done it, you can the standard form you also did in Form 1 math. So I will also not do. This is what I wanted to do now. The oil drop experiment. The oil drop experiment, you know what a molecule is. This experiment is used to determine the size of a molecule. So you know what a molecule is like. I know you've learned this in chemistry. Like the other day, you were just learning about the symbols in chemistry. And you said water is H2O. So this is a molecule. Like oxygen, it's written that way. Like hydrogen is written this way. So this is a molecule of hydrogen, this is a molecule of oxygen, this is a molecule of water, okay? So you've learned about these molecules. They are majorly learned in chemistry. So this experiment is used to determine the size. You know, now if somebody's telling you the air we breathe is comprised of millions and millions of molecules, that means a molecule must be very small. But then this experiment will be used to determine the size of a molecule. Yeah. Like water. The water you drink is comprised of millions and millions and millions of molecules of water. This one, the H2O. Millions and millions. So it means a molecule must be very small. You see. So this experiment is used to determine. Yasmin is still here. I think you need to be admitted to the other class. I've done that. Just up and join. Yeah. So this experiment is used to that. It's used to do that. So what you do, let me explain to you what this experiment is, how that is done. So you take a drop, just one drop of oil, which is considered to be spherical. Actually, that is one of the assumptions. Spherical in shape. Actually, it's considered the drop. We just pick one drop and then we allow it to drop on the surface of water. So this is water. So there is a drop on the surface of water. Now, this molecule, when it breaks on the surface of water, what will happen to it is this. Actually, this water did not capture last time. What will happen is this. Oil is an impurity. It will break the surface tension of water. So the surface tension here has been broken or reduced. It will reduce the surface tension at the point, and therefore the surface tension on the sides will pull the molecule further away from the center, yeah, uniformly. So what will happen is that the oil will spread on the surface of water like that, forming a circular patch. Forming a circular patch. This patch will have some thickness like that. Yeah. So that each molecule occupies its own space without any other overlapping on each other. So that is, so every molecule will occupy its own space. So that what will that mean? Let me show you what that will mean. That will then mean, so this is what's happening here. Since a molecule is so small, so small, this thickness, you may not see it. Yeah. But this patch is assumed, the patch is assumed to be one molecule thick. The patch is assumed to be one molecule thick, okay? So what does that mean? So these are molecular. So we call this the thickness. Now this thickness, because this is circular, it will form something like a cylinder. This way. So this is the thickness of an oil molecule. The one that you are seeing here. So I can use some technique to help me determine the diameter of the oil molecule. This one here, diameter. So with the diameter, I can get the circle. I can get the volume. So volume of the patch, volume of the patch is equals to volume of the sphere. So volume of the patch is cylindrical, so we use pi r squared h, but our h is the thickness of the oil molecule. Should be equal to the volume of the sphere that was dropped on the surface of water, which is 4/3 pi r. Fact should be this one. This other one is the one that should be capital because it is larger. So r squared and then 4/3 pi r cubed. So how am I going to determine the thickness? So that means T, the thickness of the oil molecule, will be the 4/3 here, pi r cubed divided by pi r squared. So pi r squared here is the divided by pi r squared. Pi r squared, this one here, pi r squared here is the area of the patch. Yeah. And 4/3 pi r cubed is the volume of the sphere. So it's the volume of the sphere that spreads out to form the patch. The patch is circular and it has some thickness, which is what? Which is the same as the size. Actually, this thickness here, it has many names. Other books will call it the thickness of an oil molecule. Other books will call it the size of an oil molecule. Other books will call it the length of an oil molecule. Other books can call it the diameter of an oil molecule. In fact, it can really confuse you because even this is called diameter. Even the other one has a diameter. So when you say the diameter of an oil molecule, you must say the diameter of an oil molecule, or we also have diameter of the oil patch and we have the diameter of the oil drop. So this is a drop. This is oil drop. Oil drop. Yeah. Oil drop. Oil drop. The diameter of an oil drop, the diameter of the oil patch. And now here we are talking about the diameter of, let me highlight it in yellow. Here I'm talking about the diameter of the oil molecule. A molecule. Remember, I started by talking about what a molecule is. Like O2 is a molecule, H2 is a molecule, H2O is a molecule. Those are molecules. If you just have O, that is an atom. So when you combine an atom and an atom, it gives you a molecule of oxygen, which is O2. You've learned that in chemistry. Somebody here says something. Kindly assign me the Form 3 class Terry. Okay, noted, Terry. In a short while, that will be done. Yeah, it is done, Terry. So just tap and join. Okay. So please take note of that. So that is how we use this technique to help us determine the thickness of the oil molecule. Now I've talked about the assumptions because you'll be asked to state the assumptions in this experiment. One, the oil drop is a perfect sphere. That's why I'm using 4/3 pi r cubed. The oil patch is a perfect circle. That's why I'm using pi r squared. And then the oil patch is one molecule thick. One molecule thick. That's why we are assuming that the height of this patch is the same as the thickness of an oil molecule or the size of an oil molecule. Yeah. Or other books will say, instead of talking about the oil patch is one molecule thick, other books may talk about The oil patch is a monolayer. Yeah, a monolayer. Yeah. So how to determine this one is how. So when the oil drop is carefully put in contact with the surface of water, it spreads out to form a very thin layer, which is almost circular. This is because the oil breaks the surface tension of the water, whose particles pull away from the oil. Because you'll be told to explain what causes the spread. Why does the oil spread on the surface of water? So the explanation is already there. The thin layer can be approximately be 1 molecule thick. Those are assumptions that we have talked about. Yeah. So how do you determine the size of the size of the oil drop, the volume of the oil drop, or the diameter of the oil drop? The oil drop. Remember, we have the oil drop, we have the oil patch, and we have an oil molecule. What we are determining in this case is the diameter of an oil molecule, but you should not confuse it with these other terms. Oil patch is the one that is already spread out on the surface. Oil drop is the one that is like, maybe you can use a burette and you see water droplets. One of them is what we're calling a drop, oil drop. Yeah, oil drop. And then oil molecule is the one that you cannot see, that we are trying to determine its size. So fill 1 cubic centimeter graduated burette with oil. Count the number of drops as they are squeezed out of the pipette. Let the number be Y. If the number of drops is Y, then the average volume occupied by one drop is 1 over Y. Y is the number of drops. 1 is the volume of, you put just 1 cubic centimeter in the burette. Then you allow a number of, you allow the 1 cubic centimeter. This is the burette. So you allow the 1 cubic centimeter, whatever amount of that, of the oil, to squeeze out droplets. So you are getting the number of drops, then that will give you the volume of 1 drop. If you take the volume is 1 cubic centimeter divided by the number of drops, will give you the volume of 1 drop. So that is one technique of determining. Somebody can ask you to describe a technique that can be used to determine the volume of 1 drop of oil. Method number 2 is this. Hold a drop of oil in front of a millimeter scale using a fine wire and view it through a magnifying glass. Read off the diameter of the oil drop, assuming that it is spherical. That is one of the assumptions, that the oil drop is a perfect sphere. Its volume is given by. So you can see how that is done. I think the diagram is here. So you just allow 1 drop to hang on the opening here. 1 drop, yeah. And then you put it close to a millimeter scale, and then you view it through a magnifying glass. You will be able to tell that millimeter scale. You'll be able to tell the size. See, you'll be able to tell the size. The diameter of the oil drop. Somebody will ask you to state how you can determine the diameter of the oil drop. So even this one can also be used, this technique here. Once you have the volume of 1 drop, you can still use this technique to determine the diameter of oil of an oil drop. This one, oil drop. So once you get the volume, because the volume is given by 1 divided by the number of drops, N or Y. So you'll use the formula 4/3 pi d over 2 cubed is equals to 1 over Y. Yeah, that will still give you the diameter. It will give you the diameter. Use that formula to determine the diameter of the oil drop. But still, you can just hold a drop of the oil in front of a millimeter scale using a fine wire and view it through a magnifying glass. Read off the diameter of the oil drop. So in that case, if you are asked to describe how you can determine the volume, then use the formula 4/3 pi d over 2 cubed will give you the volume of the oil drop. So either of the questions can be asked in an exam, how to determine the diameter and how to determine the volume. So please don't confuse the two. Okay, so the oil patch, this is how you can determine the diameter of the oil patch. You can see. Why we use a lycopodium powder, that lycopodium powder is not labeled properly. So if you, as you interact with this book later on, maybe for those who have bought it already, this is book 2 physics, it's not labeled nicely because the lycopodium powder is this one here. This one is the transparent part, the one that is containing oil. This part is oil. This is oil. So lycopodium powder should be this one here. It's usually used to help us see the boundary, because water is colorless, so it will be very hard. Water is colorless, oil is colorless. You will not be able to see the boundary. So it's usually used to enhance visibility. It is used to enhance visibility so that you are able to see the boundary well. So that labeling is not done nicely. Yeah, that labeling is not done nicely. So please, you will correct on that, especially those who are bought and even those who are using it. Soft copy. So you can see there is a diagram, what? There is an example here. Okay, before we go to the examples, the application of the oil drop experiment in real life. So the oil drop experiment can be used to determine the extent of environmental damage caused by oil spillage from ships. Yeah. So if you have the volume, yeah, you'll be able to tell the size. You know, if you have the volume and you have the size, if you have the volume and you have the size, you'll be able to tell the extent of spread. It's likely to cover what distance? Yeah. Because remember, we say volume of the drop is equals to volume of the patch. Is equals to volume of the patch. Volume of the drop is equals to volume of the patch. So from there, you'll be able to tell the area. So the patch is pi r squared t. So if you know the thickness, the patch, remember I said is cylindrical, and the height of that cylinder is the same as, you'll not be able to see. We call it the patch because you can't really see the thickness. Yeah. So if you have the volume of oil, and you have the thickness, you can be able to determine this pi r squared because this is the area. So that can be able to tell you the extent of spread. How much surface does it cover as it spreads out on the surface of the sea, on the surface of the lake? Yeah. So you'll be able to tell A. So A will be equal to the volume divided by the thickness. Yeah. So you'll be able to tell the area. This is likely to cover this area, and therefore this is likely to cause such extent of damage. Yeah. So in an experiment, we estimate the size of an oil molecule of, and then I've said it's called the size, diameter. Other books can call it diameter. It has very many names. The diameter of an oil molecule, the size of an oil molecule, you know, the length of an oil molecule. I mean, it has very many names. So in an experiment to determine, the size of a molecule of olive oil, a drop of oil volume 0.12 cubic centimeters was placed. So you see, we are already given the volume. So the volume of the drop is equals to the volume of the patch. So this one is already given, so I don't need to calculate it. It is what? 0.12. It's already given, the drop. It is spherical, it is already given. We said it's given by 4/3 pi r cubed. But it's already given, the whole of it is already given. So I don't need to calculate it. The other one we said was pi. Actually, I've made a mistake. It's this one that is smaller. The diameter of the oil drop is usually smaller. The patch is the one that is greater. So pi r squared h. H is the thickness. So the whole of 4/3 pi r cubed is already given. So this is 0.12. 0. So this was placed on a clean surface. The oil spreads into a patch. You see even the area, this one here, is already given. Yeah. 6.0 times 10 power 4 multiplied by t. So you see t is going to be what? 0.12 divided by 6.0 times 10 power negative 4. Actually, we said that volume, the thickness can be given by volume divided by area. You can see you can divide both sides by this to give you the thickness. This is volume, that is area. So if you divide both sides by pi r squared, it will give you the thickness. So other books will be talking about the thickness of the oil molecule is equals to the volume divided by the volume of the oil drop divided by the area of the patch. Yeah, and that's what we are doing here. So if you do that math, you will get something like, what will you get? Yeah, it is already here, 2.0 times 10 power times 10 power times 10 power what? Times 10 power negative 6 millimeters. It's because I've just used millimeters. I've not changed. That's why even the unit here for thickness must be consistent. So the units must always be consistent. Please take note of the assumptions. The assumptions. The oil drop is a perfect sphere. The oil patch is a perfect circle. And the oil patch is a monolayer. Those three assumptions will be asked in the exam. Even next week, as we revise, you'll be seeing those questions asked. Yeah. So please take note of these prefixes and their symbols like deci, centi, yeah, milli, take note. Yeah. Mega, capital M. The reason I'm saying that is because I've seen students writing kilometer this way. But you see, kilo, the symbol is, remember physics, the conventional symbols are very, very important. Or micrometer. You see somebody writing a micrometer this way. But micro we use mu. This one is read as mu. It's a U with a tail. Written as, okay. Read as mu in Greek, but it's written this way. It is micro. Yeah. Micro means 1/1,000,000 or 10 power -6. That's why I want you to take your time and study the conventional symbols. We use them intentionally. So mega is capital M. Yeah, capital M. So it has to be capital M, mega, capital M. Yeah. Megagrams. Yeah, mega. Power 6, 10 power 6 or 1,000,000. Gigabytes. Giga. Tera. 10 power 12. Peta. So these prefixes are important. Milli. Milli is 1/1,000. So if you write milli this way, this is read as millimeter. This is 1/1,000. So if you write 1 millimeter, if you remove the first M, it stands for milli. You replace it by 1/1,000. So it is 1/1,000. 1/1,000 over meter. That's why when you multiply both sides by 1,000, you'll end up with 1 meter is equals to 1,000 millimeters. That's why we got this one from. We got it from the prefixes. So if you get it from the prefixes, it is better. Yeah, it is better. You can hardly go wrong when you master this. So at your free time, just master this. You know, now initially, we used to allow students to enter exam room with the 4-figure tables in the physics classes. These days we don't, because these ones, some of them are captured in the 4-figure table. These days you are not allowed to enter exam rooms with the 4-figure tables, except in maths. So please, if you don't master them, you have to master deci, centi. You see, centi is 1/100. So if you write 1 centimeter, if you remove this C, you replace it by 1/100. You have removed the C and replaced by 1/100. That's why when you multiply both sides by 100, by 100, we end up with the 100 centimeters equals to 1 meter. See, this cancels the other one. And that's why we say 1 meter is equivalent to 100 centimeters. So, yeah. So these prefixes used in unit conversions, if you master them, the better for you. It's usually better. And so that is what this topic is all about. You can see it is very short. It's not a long topic. So I want to take unless if you have questions on prefixes and what I have discussed about the thickness of an oil molecule, what a molecule is, the terminologies used to refer to the size of a molecule. Yeah. Any questions related to all that I've discussed from the time we started till now, you are free to ask. Otherwise, I want to take the next 20 minutes just to go through questions on this topic. Then remember, next week, we are now embarking on our general revision, the one we did. And this and the first topic will be forming part of it. Yeah. So if there are no questions, we move on. So write the following correct to 2 significant figures. So we are doing A only. A only. A only first. I'm doing A only, then we'll go to B. Okay? So A, I want you to send the answers to all this. A, answers to Roman 1, A Roman 1, A Roman 2, Roman 3, Roman 4, Roman 5. All of them right away. Significant figures, 2 significant figures. Roman 1, 2, 3, 4, 5. Just type. As a single text, please don't send us very many messages. Like you send the first one again, it will be so confusing. Like I'll not even be able to read them. So please send as a single text. You type Roman 1, answer is this. Roman 2, answer Roman 3. So we are giving the answers to 2 significant figures. Please type, 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 type. Now it is time to type. I've talked for more than enough number of minutes. Now it is our time to try and implement some of the things that we've been discussing from the time we started on Tuesday till now. And see, we have about 22 minutes, which is enough time. I'm waiting for you to type. I'm giving you just a minute only. How far? If you're almost done, please type almost. If you're stuck, facing challenges, not able to navigate, please also just type in the chat so that I get to know where you are. Either way, you have to type something. Type something. Type. Whether you are almost concluding, you are stuck somewhere, it's confusing, it is challenging. Hey. No one is typing anything. Type something, please. We are typing. Pretty Gracious did it. Remember, we are rounding all of them off to, we are writing all of them to correct to 2 significant figures. So we are starting with the, I can see Katie Gracious. So what Katie Gracious has done is what I wanted you people to do. Yeah. This is what I wanted you people to do. You see now the way they are written there. Like all the 5 answers are sent as a single text. You see, that is exactly what I wanted all of us here to do. I can see only one person has sent. All the same, this is feedback. So let's do it together now that time, you don't have so much time. You only have very few minutes remaining. So the first one is 7, 3, 2, 1, 7, 6, 9. So we are supposed to round off to 2 significant figures. Now, significant figures are counted from the first, we start from the first non-zero digit from left to right. The first non-zero digit, like our first non-zero digit in this case is 7. So we count 1, 2. Then you draw the cutoff line. Now, the number after the cutoff line can fall in the upper category or lower category. Upper category are the numbers from 5, 6, 7, no digits, 8, and 9. Lower category, this is upper. Yeah, upper category. Lower category, we have numbers 0, 1, 2, 3, 4. So the digit after the cutoff line can fall in the upper category or lower category. Now, if our digit after the cutoff line falls in the upper category, we increase the digit before the cutoff line and reduce the digits after the cutoff line, all of them to 0. If the digit after the cutoff line falls in the lower category, the number before the cutoff line remains the way it is, but all the digits of the cutoff line will be reduced to 0. Yeah. Let me repeat. If the digit after the cutoff line falls in the upper category, we increase the digit before the cutoff line by 1 and reduce all the digits after the cutoff line to 0. If the digit after the cutoff line, falls in the lower category, this digit before the cutoff line will remain the way it is. But you still have to reduce all the time. You still have to reduce the digits after the cutoff line all to 0 after you've rounded off. Like this one is going to be approximately equal to 73. And then you reduce, how many digits are they? 5. Yes, zeros like that. So we have not increased 3 by 1 because 2 falls in the lower category. Remember I said the lower category digits we have 0, 1, 2, 3, 4. Upper category digits we have 5, 6, 7, 8, 9. Yeah. So you just check whether the digit of the cutoff line falls in the what? In the lower category or upper category. And of course, as I've always said, you need to group them in groups of 3 it makes it easier for you to read, like this is going to be 7,300,000. Two significant figures. Yeah. Remember, again, I've said significant figures are counted from the first non-zero digit from left to right. So we have the second number, 6. So that is the first one. So Katie Gracious got it right. The second one is, the second number is 6, 6, 5, 7.65. Yeah. So we count 1, 2. You draw the cutoff line. You can see the digit of the cutoff line falls in the upper category. So we'll increase this by 1, 5 by 1, and then all this will reduce them to zeros. So that is 66. We have increased 5 by 1 to make it 6. And then all these others after the decimal point, we will reduce them to zeros. So 0, and then 0.00. Now, zeros after the decimal point, normally they don't count that much. Yeah, so you can ignore them. So this is going to be 660. Just like that. And you can see Katie Gracious got it right. When we move to 27 point, so we are moving to 27 point. We have 27 point. So you do the same thing. That 27 point what? 0.002. You do the same thing, you count 1, 2. You draw the cutoff line. The digit of the cutoff line is 0. 0 falls in the lower category. So nothing happens to the digit before the cutoff line. So it remains to be 7. But all the time I said, after the cutoff line, reduce all of them to zeros. So 0.000. And then I said the digit of the cutoff line, after the decimal point, normally they don't count. The zeros, please take note, it is the zeros after the decimal point. The zeros after the decimal point, the zeros after the decimal point, normally they don't count that much, so you can ignore them. So the number is 27, and that is what Katie Gracious got. Let me move on to which number now? The third one, which is 0.0008996. Yeah. 8996. So I will count. Remember, the rule still remains. The significant figures we count from the first non-zero digit from left to right. So we will not count this. We will not count this because that is 0. We will not count this. We will not count this, but we'll count 1, 2. Then we draw the cutoff line. You look at the digit of the cutoff line falls in the upper category. So we'll increase the digit before the cutoff line by 1. So this is approximately equal to 0.000. Now, if you increase this by 1, it will be 10. So you only write 0 there, and then you carry that one to the next one. So that will make this one 90. So 90. Then all these will reduce them to 0, 0. Yeah, like that. So remember, 0 is considered to be significant if it falls between 2 non-zero digits. Now, this 0 here is not significant. This is not significant. Even this is not significant. This is not significant. This is significant because it's a non-zero digit. Even this 0 here is significant because we are told. There are instances when even though 0 may not be in between two non-zero digits, but still that 0 will be significant. And that such a case is like this one here, because we are done what? We are being told. How many significant figures? 2. And the first one is which one? 9. And therefore this 0 is significant. So as you erase the last zeros, remember I said the last zeros after the decimal point, they normally don't count. So you cannot erase this. This one will remain. So I will only erase these 2. These 2, I will erase them. They don't count that much. Even this one won't have, like it could have not been very important, but because we are told it is significant, we have to maintain it. So this number is approximately equal to 0.00090. So the first zero, not significant. Second, not. Third, not. But the last one there is significant. Why? We are told. Yeah, we are told it is. Okay. Fine. Somebody's asking, teacher, what about which one? What about oh yeah, we skipped a certain number there. Yeah, that is very good, Katie. There is Roman 4. Yeah, so Roman 4 is the one we are doing now. Roman 4 is 0.001895. So you do the same thing. You just count from the first non-zero digit. So this one no, this one no, this one no. So I count from 1 to, you draw the cutoff line. The digit of the cutoff line falls in the upper category. So I will increase the digit before the cutoff line by 1. So we have 0.001900. The last zeros after the decimal point will not count much, so you ignore them. So this is approximately equal to 0.0019. And that is the answers. Those are the answers that I was given by Katie Gracious. So Katie Gracious, you only failed the last one. That number 5. And that is why it is important you attend these lessons. By the way, even if you feel that what you are going to learn, you know, it's always important you attend, because in one way or the other, you will still learn something that will help you somewhere. You never know. Yeah. Like Katie Gracious almost got everything right except the last one. So can we attempt B? You can see we have 7 minutes. B. We are now attempting B, number 1B. We are doing number 1, but B. Very fast, please. Number 1B. Roman 1, Roman 2, Roman 3, Roman 4, Roman 5. The difference between A and B is that A, 2 significant figures. B, 3 significant figures. So the same numbers. Hurry up. Just 1 minute, you should be done. And see somebody still Katie Gracious only. You people. You people now. It's only Katie Gracious who was sent again. How about the rest? How about the rest? And I can see Katie Gracious. That is good. You have corrected the previous mistake you made. That is what we call learning. Yeah, at least now I can see some more people have sent, like Purity, Renata. Yeah, this is encouraging. Yeah. I can see now we have more people like Renata. Though Renata, you've only sent one. I said you're supposed to send us a single text, all of them. Yeah, I can see Julie, Shavana. Yeah, now at least we have more people. Though Julie, Shavana, you've only sent like number 1, number 2, number 3. And number 4. Only. Yeah, okay. Okay. Yeah, so now, let me do it. Let's do it together now. So if you start with the first one, let me do it here. So I want to start with the first one, Roman 1. Remember, we are doing B Roman 1. We are correcting them. We are correcting these numbers to how many significant figures? 3. So the number we have is 7321769. So we said previously that significant figures are counted from the first non-zero digit from left to right. So 1, 2, 3. Then you draw the cutoff line. You look at the digit of the cutoff line. If it falls in the category or the upper category, increase the digit before the cutoff line by 1. If it falls in the lower category, leave the digit before the cutoff line the way it is. but then all the time reduce the digits of the cutoff line to zeros. So that is 7 approximately equal to 732,000. Yeah, which is 7,320,000. I think that is what some of us, on senior, you failed that because you forgot. The only time you remove the zeros is when they are the last zeros after the decimal point. There is a decimal point and they are last, the zeros are appearing last, the very last. When I say last, on your farthest right, huh? Yes, that's what I mean. So that is the mistake you made. Ryan got it right. Julie Shavana got it right. And Purity got it right. And Katie Gracious definitely got it right. Then now, we move on to number Roman 2. So Roman 2, we have 657.65. You do the same thing. 65. We count. Let me count. Yeah. 1, 2, 3. 3. Cutoff line. The digit of the cutoff line falls in the upper category. I will increase this digit by 1. So that is 6, 5, 8. And then we reduce the digits of the cutoff line to zeros. Remember, I said these zeros, last zeros at the decimal point, they don't count. So this is approximately equal to 6, 5, 8. Yeah. Anyone who got that? Go on, senior got it right. Who else? Julie Shavana, you can see you also got it right. Oh, I think somebody here yeah, on senior got it right. Julie Shavana, you got it right. Somebody else is who? Trying to get Katie Gracious got it right. Yeah, exactly. So let's move to number 3. Roman 3. Roman 3 is 27.002. So we said the significant figures are counted from the first non-zero digit from left to right. So 1, 2, 3. You draw the cutoff line after that. 1, 2, 3. My pen. 1, 2, 3. So I draw the cutoff line there. The digit after the cutoff line falls in the lower category. So this will remain the way it is. Then after that, you'll always reduce the digits of the cutoff line to zeros. So 27.0. Then 0, 0. You see now, these zeros after the decimal point, they don't count, yes. But now this 0 here is significant. Why is it significant? Because we are told. We are told. So we counted it as a significant figure. We are told. That is the only reason why that 0 is significant. Otherwise, all these other ones, I will erase them because they are not counting that much. The only reason I've left the first 0 here is because we are told that it is significant. So this is approximately equal to 27 point what? 0.0. Yes, 27.0. Yeah. Then we move. I don't know whether we got it right. Yeah, Purity got it right. Who else? Onsinio failed that one. You failed to indicate the decimal point. Ryan got it right. Julie Shavana got it right. Purity got it right. Katie Gracious got it right. So we are getting better. This is so encouraging. It is really, we are really getting better, which is really, really encouraging. So we have the next one is 0.001895. 1895. So what do? We do this one. This is the last one we are doing, and then we end. Don't exit before you finish. I can see some already exiting. So we'll not count this 0 is not significant because we said from the first non-zero digit left to right, not significant, not significant. So I start from 1, 2, 3. Then you draw the cutoff line. Look at the digit of the cutoff line. It falls in the category, in the upper category, yeah? So we increase the digit before the cutoff line by 1. But if you increase 9 by 1, that will be 10. So we write 0, we carry 1. Then that one will write it here. And then this one will remain. So this is approximately equal to 0.00190. Then we reduce the digits of the cutoff line to zeros. Now in this case, this 0 is not counting that much, so I will omit it. Even this one won't have, it will not be very important, but we have been told that it is significant, so we have to retain it. So this is approximately equal to 0.00190. The last one, before we end, can see some of us are already exiting. The last one before we end is Roman number 5, which is 0.008998996. So what we do, we will not count this, we will not count that, we will not count this, we will not count this. I'll count from 8, 9, and 9. You draw the cutoff line. The digit on the cutoff line falls in the upper category, so you increase the digits, the digit before the cutoff line by 1. If you increase 9 by 1, it will be 10. You write 0 carry 1. You bring it to the next one, will be 10, 0 carry 1, and then this is 9. So we have this approximately equal to, so we end approximately equal to 0.000900, and then the 6 reduces to 0, but this one will not count that much. The last zeros normally don't count that much. The only reason why this last 0, the 2 here are important, are significant, is because we are told. So this is approximately equal to 0.000999900. And so that is all for the day.